Okay, so I'll start now the seventh lecture of this series about the science of light. I will talk today about the concept of entanglement. Entanglement is supposed to be the strangest feature of quantum physics. It's a statement which says that if two systems have interacted, even when they are separated spatially, they remain connected by a kind of immaterial link which correlates the result of measurement performed on the two systems. Mathematically, it means that the quantum state of the two systems cannot be expressed as a tensor product of two independent states for the two systems. Mathematically, you have a superposition of products of states, but you cannot consider the system as two systems independent from each other. So this is called entanglement, and this concept has been known since the beginning of quantum physics. In fact, we will see that the ground state of most atoms and molecules are entangled states of electrons. And of course, it does not have the same meaning when you look at entanglement between two particles which are very, very close apart, like in an atom or in a molecule, or entanglement, is a phenomenon which occurs in systems which are separated by large distance. So we'll discuss all these points today. We will see also that if you have two systems, and if you make a measurement on one of the systems without looking at observable of the other, you can no longer, to predict the results, you can no longer describe the systems that you are looking at with his quantum state. You have to define a new concept, which is called the density operator. And all the predictions are based on the density operator and no longer on a quantum state when two systems are entangled. We will also see that entanglement is very closely related to the notion of complementarity that I have discussed before, that you need also to understand entanglement in order to understand what is a quantum measurement, because in a quantum measurement, in the first stage, you entangle the systems that you want to measure with an apparatus which is going to extract the information from the system. And we also see that entanglement is related to the notion of decoherence, the fact that quantum systems lose their quantum coherence because they get entangled with their environment. So I will discuss all these features, and I would like to have time at the end to discuss one of the most strangest aspects of entanglement, the fact that even when the systems are separated by a large distance, the measurements that you do on the different parts are completely random, but it's a randomness which is correlated between the 2 points. This is a problem that Einstein had discussed in a famous paper in 1935, and Einstein said that this kind of experiment was the illustration of the fact that quantum mechanics could not be complete. And we'll see that, in fact, tests have been made. There have been thought experiments which have been thought about, and it has been shown that Einstein was wrong. In fact, Bohr's version of quantum physics has been vindicated by this test. And I will end up in the end by describing to you the possibility of teleportation, which is based on the properties of entanglement, and which is very useful in quantum information science. So what is quantum entanglement? So the definition is quite simple. When you have two systems, A and B, the most general state you can write with these two systems is written here. You take a basis in Hilbert space of A basis in Hilbert space of B. You make the tensor product of these two bases, and you write the most general superposition of these states. Now, the system is said to be entangled when you cannot factorize mathematically, when you cannot factorize this as a product of a quantum state of system A by a quantum state of system B. And I will give you a few examples. The first example I can give you is related to what we discussed at the beginning of this lecture when I talked about the Young double slit experiment, and I told you that one of the thought experiments that Bohr and Einstein were discussing is what happens when one of the slits is moving. And you see here, so I show you here the wave function, the quantum state of the particle, which is a superposition of the part of the wave function corresponding to the particle going through the upper slit and the part of the wave function corresponding to the lower slit. At the beginning, before the system has interacted, you get this state, tensor product with the motionless state of the slit. And after the interaction, you get into this system, this state in which the particle, if the particle has gone through the upper slit, it received a kick, a momentum kick when it crossed, and the slit recoiled in the opposite direction. On the other hand, if the particle went to the lower slit, nothing happened to the upper slit, and you have this part. And you immediately see that this wave function, this quantum state, cannot be separated as a product of a quantum state for the particle time a quantum state for the moving slit. So this is a very simple example of entanglement. Here I give you two examples of entanglement coming from atomic physics, and they relate to the simplest of all possible atoms, helium and hydrogen. Let's start with the helium atom. You have two electrons. Each electron has a spin. In the ground state of the helium, the two electrons are going to the lowest possible orbital state, which is an S state, a state which has a total symmetry of the angular momentum is 0, and so the wave function is spherical. But if you put the two electrons here, they have the same orbital state, so there's the wave function of the ground state is symmetrical by electron exchange. So the spin state has to be antisymmetrical because the whole wave function has to be antisymmetrical because they are Fermions. Another way to state it is to say that if the two electrons are in the ground state, they must have opposite spins because they cannot be in the same orbital plus spin state. So you see immediately that the ground state, the spin part of the ground state is this wave function plus minus 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 plus, which is the singlet state, and it is an entangled state. Here, the entanglement does not come from the interaction. The entanglement comes from the exclusion principle. So it's a special case. But I can give you another example, which relates this time to hydrogen. In hydrogen, you have two spins. You have the proton spin and the electron spin. In the ground state, the electron is on the first orbit, but the two spins, the proton and the electron spin, interact through magnetic forces, and the energy is different whether the two spins are like that or like that. And in fact, the ground state corresponds to this state where the two spins are opposite, and this state is again an entangled state. So the ground state of hydrogen is the entangled state in which the proton is up and the electron is down, or the reverse. And this is due to the magnetic interaction. So this has been known for a very long time. Now I take a more general case, and I want to tell you that entanglement can be due to two different physical phenomena. One is the interaction between two systems. So here you have two parts, A and B, and before they interact, the wave functions, the quantum states are independent. So you have a tensor product, independent states for the two particles. So suppose that they collide and then they separate again. And usually, in the end, the two wave functions are entangled. You cannot separate them as it was at the beginning. And I give you just one example. I take the case where the interaction is precisely what you have in hydrogen. I take a Hamiltonian, which is a superposition of this part. And you see immediately that if this part acts on first spin down, second spin up, it will replace it by the other one, and reciprocally. So this is an interaction which flips the spins. And I let you do the exercise. If you start with this Hamiltonian, and if you put this Hamiltonian in Schrodinger's equation, you find the general solution, psi of t oscillates between this state and the other state, with a cosine and sine function, which are proportional to the coupling constant, which is the energy that I have put here, epsilon naught. So you see that you have a kind of flip-flop between the two. And if you are at half flipping time, the system is again in a superposition. So you can prepare, starting with a situation like that. After some time, you get into a superposition state between the two. And if you wait twice this time, the system disentangles again, and you have a succession of entanglement and disentanglement as time is going on. So this is entanglement due to interaction. But you can also have entanglement due to measurement. So here I start with two systems which are separated, and I perform a joint measurement. What does it mean, a joint measurement? It means a measurement of an observable, which is a common observable of the two, which is not just an observable of A or B, it's a common observable of the two. For instance, you can take as a common observable the total spin. If the two particles have spins, you can measure the total spin, which is a common observable of the two particles. And here I show you on this slide that if you measure the total spin, you start with a state which is separated and you get an entangled state. For instance, suppose that you have prepared the system with spin up, first particle spin up, the second particle spin down. So this is not entangled. You have one quantum state for the first particle, tensor product with a state for the second. Now you can always write this, expand this as this superposition. In fact, there is an error in the notes. I have a square root of 2 in the note. In fact, the 1/2 and 1/2. You see immediately that if you add this, these terms cancel with this one, and you get twice pressed down, which is just pressed down. So you see that this state can be written as a superposition of a symmetric and antisymmetric state. Now, we learned last time that the symmetric state has spin 1 and the antisymmetric state has spin 0. So assume that you measure the total spin. What will you get? With probability 1/2, you will project on the entangled state with the plus sign. And with probability 1/2, you will project into the other state. So you see that a measurement of a joint observable let's you at the end with an entangled state. Of course, you don't know which one you will find until you make the measurements. The probabilities are 1/2, 1/2. But once you have found the result, you know which entangled state you have prepared. So this is entanglement produced by measurement. Now, why do we need the density operator formalism? I will start first by describing you what the density operator is for a pure state, for a quantum state, as the one we have been studying up to now. When you have a quantum state of a global system psi s, you can always associate to this quantum state the projector on this state. What I have written on the right, P S here is just the projector on the quantum state. So each quantum state has its projector. What is the projector? The projector is a Hermitian operator, which has two eigenvalues. If the state psi s is the eigenstate, of course, with eigenvalue 1, and all the states which are orthogonal to psi s are eigenstate with eigenvalue 0. So the projector is a very simple operator. It has two eigenvalue 1 and 0. Eigenvalue 1 for the state you are considering, and eigenvalue 0 for all the orthogonal states. So what is the interest of this operator? This operator is called the density operator. And now I just want to express with this density operator the postulates of the quantum measurement. So suppose that I want to measure an observable, and I expand this observable on the basis of eigenstates. So AI is the eigenvalue, and PI is a projector on the eigenstate, on the eigenspace with eigenvalue I. It can be non-degenerate or it can be degenerate, it doesn't matter. You see immediately that PI can be written as a projector on all the states which have the eigenvalue AI. So I have another quantum number which I call alpha in case of degeneracies. What is the probability to find the result AI when you make a measurement? PI, this probability is just the sum of the scalar product of psi with I alpha. This is the definition, this is a postulate of measurement. But you see immediately that you can write this expression, you can expand it and write it as I alpha psi, get psi, then bra psi I alpha. This is exactly the same thing that this. And you see now that you have sandwiched psi psi between I alpha and I alpha and sum over alpha. What is psi psi is a density operator, and you have taken all the diagonal elements corresponding to the subspace of this eigenvalue. this is a partial trace. This is a trace of this density operator over the inside the eigenspace corresponding to the eigenvalue I. So you write this, you say that the probability Pi is just a trace of projector I times rho S. For the time being, I have done nothing else than rephrase the postulate of quantum physics with this psi S density operator. So there is nothing new up to this point, but this will become useful and interesting when I will be considering measurements which are performed on a part of a system which is coupled to another one. And then the density matrix, the notion of density operator, will become relevant. But you see, up to now, the density operator is very simple. It's an operator which has just two eigenvalues, 1 and 0. So now look at what happens if I have two systems, A and B, and I focus on A. I have no possibility to look at what happens on B. So I want to measure quantities which are of the form OA, operator acting on A, tensor product with the identity on B. What does it mean, identity on B? It means that I do nothing on B. I just B is spectator during the measurement. And you see now that the projector on the eigenspace Pi now is written like this. You have a double sum. You have to sum over the possible degeneracies inside A, and you have to sum over a basis on B because you don't make any measurement on B. So I call beta the parameter which label the eigenstate inside the eigenspace I of OA, and I call mu any basis in B. And now I apply the same postulate. What is the probability to obtain the result I if I measure A without looking at B? So I do exactly the same thing. And you see now that you have to sum over beta and mu. And I can write this sum under this form. I can isolate this quantity, which is the sum over mu of mu psi psi mu. What is this quantity? Psi psi is the density operator of the global system. And I trace it over the variable, over the space of B. So it's a partial trace. It's a partial trace of the density operator over B. So the bracket is a trace over B of the global density operator. And I can write this quantity, I write it trace over B of rho S. And you see now that the postulate of measurement says that if you have rho A, which is trace of B of rho S, if you want to have the probability Pi, you just now trace over A of Pi rho A. So you have exactly the same formula as before, but now it's not a formula which implies the global density operator of A plus B, but you can express everything in terms of the density operator of A alone. So you see, and symmetrically, if you want to make a measurement on B alone, you have to trace over A rho S, and you get rho B, and rho B will give you all the information about the result of possible measurement on observable in the B system. So finally, we have this formula, and the expectation value is given also by the same formula as the one we had before, but now the result we get is that the expectation value, the average of all possible measurements, if you do the experiment again and again on an observable of A, is a trace of OA rho A. So rho contains all the information you need to predict results of experiments performed on a part A of a system which is entangled with a system B. So apparently nothing is new here, except that rho A is no longer a projector. We will see that the density operator rho A has several eigenvalues, not only one, different from 0. And this is something that I want to discuss, the physical interpretation of. So what is rho A? Rho A is an operator acting on A. It's an operator which is Hermitian, because everything is Hermitian here. So we know that the eigenvalues of the Hermitian operator are real numbers. And more than that, here there are positive real numbers. Why? Because these numbers are probabilities. So we have now an operator, and we have this formula. If you sum over all possible results, all the I results, of course, you have to compute the trace of rho sum over all the projectors. The sum over all the projectors is 1. So you have the trace of rho A, and the trace of rho A has to be equal to 1. This is just expressed that the probability of all possible results has to be equal to 1. So this is this density operator of the system A is a Hermitian operator with a trace equal to 1. What else can we say? So you can express it in a basis which is diagonal. You can always diagonalize a Hermitian operator. So in a diagonal basis, you will have this formula. Rho is the sum of projectors on functions which I've called phi I with a constant lambda I. The lambda I are real positive numbers. So density operator has a diagonal, has a form on a diagonal basis of positive numbers. How can you interpret these numbers? You can always say, okay, I don't know in which pure state I am. There is a probability lambda I to be in such pure state, a probability lambda J to be another pure state. And when I compute the probability of results, I have to ponderate what I would get if I were in the first, the second, or the third one, multiplied by lambda I and sum over lambda I. This is what the formulas that I showed you on the previous slide mean. So the interpretation of this partial density operator of the system A is just to say, once the two systems are coupled, I lose some information. The information which are in the correlation, the two are lost. And so I get less information about the system A. And the only thing I can say is that I have probabilities that A might be in different quantum states with the probability lambda. So this is what a density operator is about. And I also insist on the fact that the lambda being positive numbers, you have no interference possible. The lambda do not, the probabilities do not interfere. What interferes in quantum physics are the probability amplitudes, which are phases and which can give rise to interference effects. Here, these are just statistical probabilities. So you see that now you have two kinds of randomness in quantum physics. If you know the quantum state exactly, the only randomness is quantum. The fact that a measurement gives a random result. Here you add another randomness which comes from a lack of knowledge on one part of the system because it is coupled to another one and you don't know what is happening in the other system. This second randomness is given by positive probabilities and they don't interfere with each other. So that's an important point. Now, when I give you a density operator, how can you recognize whether it's a pure state or a mixture state like that? But the criterion is very simple. You compute the trace of rho square. And it's very simple to demonstrate why. If you have only one eigenvalue, which is equal to 1, and all the others are 0, when you square, you will get the same result. And the trace of rho square will be 1. If, on the other hand, you have at least 2 eigenvalues which are different from 0, you see immediately what will happen. The trace will be equal to the sum of the lambda I squared. And the sum of the lambda I squared is smaller than the sum of lambda I all being squared. Because if you square a sum of lambda I, you will have cross product of positive lambda, which will increase the result. So you know immediately that you have a necessary and sufficient condition. Trace of rho square equal to 1, you are in a pure state. Trace of rho squared smaller than 1, you are in a mixture. Okay. Next step, now I want to give you a very simple example. I come back to a spin 1/2. I remind you that when we started with a spin 1/2 last week, I told you that any state, any pure state of a spin 1/2 is mirrored on a sphere, the block sphere. If you take a point on the block sphere, it gives you a theta and a phi, and you get a direction, and the pure state is just the eigenstate corresponding to a spin pointing in that direction. Now, what can you say about a mixture of state. What is the density operator of a spin? Now, the result is very simple. It's very simple to understand what happens. It will be a density operator in a Hilbert space of dimension 2. We know that it can be expanded on I, the identity operator, and the Pauli operator sigma x, sigma r, and sigma z. So I give you here the most general expansion here, and you know, moreover, you know that all the A must be real numbers because the matrix has to be Hermitian. And you know also that A naught is equal to 1/2 because the other Pauli matrices have a trace equal to 0. The trace can be only in the first term. So A naught is equal to 1/2, and the AI, X, Y, and Z are real numbers. So, and what are these real numbers? I give you a very simple exercise. Compute the expectation value of sigma I. You write this and you find it's equal to 2AI. Why 2? Because you have to take the trace of rho I, rho j, and sigma I, sigma j, and it's twice delta ij. So with this property of Pauli matrices, you find that the expectation value of sigma I is equal to 2 times AI. So if I take all this into account, I write at the top here, I can say that AX, AY, and AZ are the 3 components of a vector along X, Y, Z, and I call it the block vector, P block. And you see what I have demonstrated is that the most general density operator is 1/2 I plus the scalar product of P block with the sigma matrices. Sigma X, sigma R, and sigma Z. If I want to write it as a 2x2 matrix, I get what I have here. So I made a mistake. There is a minus sign here and a plus sign here. You get here this as a combination of Px, Py, and Pz as matrix element of this density operator. Now I'll let you to do as an exercise to compute the trace, to compute rho square and take the trace of rho square. And you find that the trace of rho square is equal to 1 plus p squared over 2. So this has to be, what can we say about that? We want this to be smaller than 1. So this requires that p squared has to be smaller than 1, smaller or equal to 1. So the norm of the block vector has to be smaller or equal to 1. And this will make the connection with what I explained to you last week. You see that the most general density operator is represented by a vector inside the block sphere. And if you reach the block sphere, you are in a pure case. So the pure case are the points in the block sphere, and all the points inside the block sphere represent density matrices of mixtures. Now, the most mixed state is, of course, if you take p equals 0. If you take p equals 0, the density matrix is just 1/2, 1/2. It means that you have absolutely no information. The density matrix tells you nothing. It's just the identity operator. It tells you nothing about the state. If you are on the block sphere, you have the maximum possible information. And in between, you have a mixed information due to the fact that you don't know in which pure quantum state you are. Now, I would like on the next few minutes discuss the connection of entanglement with complementarity, of entanglement with measurement, and of entanglement with decoherence. So let's start the connection of entanglement with complementarity. And I start again with this kind of generic experiment. I do an interference experiment, and I suppose that there is something, there is an apparatus which allows me to get some information about the path. So what I described before was this movable slit, but it can be anything else. Any measurement device M, which give you information about the quantum path followed by the particle. So what is the most general wave function of the total system A plus M? You have one, this is one, the part corresponding to path 1. This is the part corresponding to path 2. There is a phase between the two, which is the phase that we want to measure by doing the interference experiment. But you see that if you are in state 1, you couple to a state of the measuring device psi M1. And if you are in state 2, you couple to another state, which I call psi M2. And you see exactly immediately what happens as soon as you try to find out, and you have some kind of spy or watching mechanism system which will give you some information about the past, you entangle the two systems. You get an entanglement between the particle which you want to see the interference of and this meter. So let's apply the rules. The interference signal, of course, in the end, you will, for instance, compute the probability to find the particle at point X on the screen. So what you have to compute is the probability to get a given result on the system A, not on the meter. You don't look at the other system. So you have to take the partial density operator for the system A. So I show you here how it works. And you find that this partial density operator has two square terms, which is just 1/2 psi1 squared plus 1/2 psi2. Yes, 1/2. No, you get 1/2 psi a1 psi a1. This is just a projector plus 1/2 psi a2 psi a2, another projector, and then you have the interfering term, and you see now that the off-diagonal terms are multiplied by the scalar product of the two states of this device, which give you information about the past. So you see that the interference is multiplied by the scalar product of the two final states of the slit, moving slit, for example. So, and this is the partial density operator. So now, with this partial density operator, you want to compute the probability to find the particle at point X. So you just apply the postulate that this probability is just a trace of the projector on X time rho A, which is just the expectation value, the matrix element of OA between X and X. And I developed it here. And you see that the interference comes, of course, from this term, because it is the only term which has a phi, a term depending on phi. And you immediately see this very interesting result. The interference term is as a contrast, which is the scalar product of the two final states of the moving slit or of the device, which tell you something about the past. So you see that two different things may happen. If this device has no coupling to the system or does not give you any information, psi m1 and psi m2 would be equal, and this cross product will be 1. So you have a large contrast. Now assume that psi m1 and psi m2 are orthogonal to each other. It means that you have a maximum information. If you find this result, you know that you went through pass 1. If you find this result, you know that you went through pass 2. Psi m1 psi m2 is equal to 0, the fringe disappears. So you see that there is a complementarity between the visibility of the fringe and the amount of information you have in the system M. And this is what complementarity is about. You see that it's no longer something which is vague and which is a statement with words. This is something which is mathematical in this kind of expression. And what you see also, which is very important, is you don't have to measure or to look at what happens in the environment. The mere fact that in the environment, the two states get orthogonal to each other is enough to make sure that you won't see the fringes. So you don't have to make an active measurement. You just have to, this fact that you have that something happened in the other system, which put the two states orthogonal, and then you have no fringes left. So this is complementarity. And you see that you have the fact that you get information in the other system decrease the contrast, decrease the coherence of the two passes. Something more general will happen in a moment when I will be talking about an environment system which is coupled to a reservoir made of a lot of particles in which information can be lost. Here again, we will see that very efficiently and very quickly, all coherence between different passes in the system disappear due to the coupling to the environment. And this is called decoherence, and I will talk about it in a moment. Now let's discuss the connection between entanglement and measurement. what is a measurement on a quantum system? Usually we talk about measurement on a microscopic system. So here I represented an atom, and I couple this atom to a meter. And of course, the meter, in the end, the meter has to be macroscopic because you want to measure something. So you have either to see the motion of a needle on a meter, or to read something on a digital screen, you need to have a macroscopic information in the end. So what I want to discuss here is how you couple the microscopic system to the macroscopic information that you get in the end. So again, I assume I start with a system psi, which is in a pure state, which is in a superposition of eigenstates of an operator O with amplitude alpha I, and I want to measure O. So if I measure O, I will find one of the eigenvalues, and then it will project, it will collapse the system in one of the eigenstates of this sum of states. And I do that by coupling my system to a meter, and I call zeta 0 the neutral point of the meter. Assume that before the interaction, the meter is here, and then it will go left or right, or it will move along a line or along a circle to give you the information. So how can you make a coupling which realizes this conditional dynamics? There are several models you can construct, but the simplest one is what I show here. Assume that the Hamiltonian of the coupled system is proportional to OA times the momentum of the meter M. I assume that the meter M is just a point moving on a line, and I call PM its momentum. So if you take a coupling with the G is just a coupling constant, which is an homogeneous to an energy, times OAPM, I remind you that P is a generator of translations. And so if I expand OA on the basis of eigenstate of A, I will make a translation which will be proportional to the eigenvalue. And so if I have different eigenvalues, it will give different translation. It is exactly what I need. I need to have a coupling which moves the needle by different amounts depending upon different eigenvalues. And this is what I have written on the right part of this slide. You see the evolution will couple these two states which are at the beginning, which are separated, and give this result, which will give me an entangled state, because for the different AI, I will get different shifts of my meter. And so you see that a measurement entangles the system that you measure with a meter. Then you you look at the meter, and depending upon where the meter is, you will collapse the system into the corresponding eigenstate. So the second part of the measurement is to measure the meter, and then you collapse the system into the correlated eigenstate. And you see, so this is quite simple. Now, if you want to enter into more details, you have to first understand that at the beginning, you cannot start with a meter which is at a well-defined point, because if it is at a well-defined point, it has a completely undetermined momentum. So you have to take a wave packet of the meter and look at how this wave packet moves. And the resolution should be such that the wave packet has a given width, and different eigenvalues should give you different positions. So you have this inequality here. It means that this, if you call delta zeta the smallest difference between eigenvalues, you see that GT delta epsilon should be larger than delta zeta. So you have to wait a time long enough so that you will separate the wave packet corresponding to different eigenvalues. So it's a kind of uncertainty relation. If you have a very small, if you want to distinguish very closely spaced eigenstate, you need to wait longer and longer times. So it's also a kind of statement that if you want to make a very careful measurement, it will take more time than if you don't need to make a careful measurement. And quantum physics contains this. So this is quite simple. Now I would like to come to the problem of Schrodinger's cat. In fact, of course, Schrodinger had been thinking about all these issues very closely at the beginning of the 1930s, and he came to very unsettling conclusions. he said, okay, let's go back to the situation that I have just described, and let's look at what happens if you want to measure a simple system, let's say spin or a two-level system, and you start with 1/√2 0 plus 1, or an atom in the excited state plus one atom in the ground state, any superposition of two states, and you couple it to a macroscopic apparatus, and then we call 0 and 1 the two states of the macroscopic apparatus corresponding to the final state possibilities. So I just do again exactly what I said before. And you see now that you will have this kind of entanglement. If the system is in state 0, it will be coupled to the 0 state of the meter. And if it's 1, it will be coupled to the 1 state of the meter. You have entanglement. So far you can say, okay, it's not a big problem. I have entanglement. But let's do the following remark. I can rewrite in a different way what happens. And you see that if you look at this system, it means that you have a coherence between the two parts of the wave function. And here it's a meter which is at one position, and this is a meter at another position. So you have a situation where the meter, which is a macroscopic object, can be at two different macroscopic positions at the same time. And this is exactly what Schrodinger discussed when he talked about this tale about the cat which is dead or alive, because he wanted to give a kind of dramatic vision of this. And he said, let's suppose that the meter is a cat. If the atom, I have a two-level system, which is an atom. If the atom is excited, nothing happens to the cat. But if the atom goes to the lower state, it triggers a device which will kill the cat. For instance, a photon is emitted, and the photon triggers a gun or triggers any little device which kills the cat. What happens if the atom is halfway in a superposition of being excited and de-excited? The cat has to be in a superposition of being dead and alive. So we come, if you couple a microsystem to a macrosystem, you come to this kind of thing that Schrodinger said is a ridiculous statement. So the cat cannot be half dead, half alive. Another way to look at this is to write what I have written here. In fact, this expression is exactly the same as this one. You can write, if you expand the four terms that you have here, you find the two terms that you have here. So you see that the entanglement between the meter and the two-level system can be written in this way. And if you write it in this way, what you see is if you measure the superposition of 0 plus 1 or the superposition 0 minus 1, you will collapse the atomic system into 0 plus 1 or 0 minus 1. And it is the same quantum state. So the question is, what are we measuring here? Are we measuring the spin along the z direction, which is given by this expression, or are we measuring the spin along the x direction, which is given by the other expression? And of course, you cannot do both things with the same apparatus because the spin along different directions do not commute. So there is something wrong here. This apparatus cannot do the two measurements. So which is the right measurement and what is wrong? And the answer to that question, to make it short, is that we forgot if you couple the system to it, if your meter is a large system, you cannot avoid considering the environment. The fact that a large system is not isolated from a lot of degrees of freedom in the environment. And this is what I try to express on this slide. What I want to make you feel is that when you cannot assume that a measurement is a question is a story between two parties, the measuring device and the system to be measured. You have a third system which watches on all this, which is the environment. For example, in the case of the cat, it's clear that if you want to have a cat alive to start with, the cat has to be surrounded by molecules, by thermal photons, a lot of things. And so to talk about the wave function of the cat is ridiculous because the cat is has a density operator from the start. So there is something wrong in the description that we made. But let's assume that you can, at the beginning of the experiment, have a pure state for the system and a pure state for the cat. And so you see that, and you see that operations they describe, if I label the state of the system by 0 and 1 and the state of the meter by 0 and 1, what the coupling is just making an addition modulo 2. If the two systems are in state 0, they stay in state 0. But if one state is in 0 and the other in 1, it goes to 1. And so the state of the measuring device shifts from 0 to 1. So what is the situation we are considering? The situation is that you have to add the environment. And you see now that you have a three-parted system. Your entanglement or your superposition is 0, 0 for the system and the meter, and you have also 0 for the environment. And if the meter is in state 1, the environment is going into state 1. So the environment is watching, and the environment is going into very quickly into orthogonal states, whether the meter is in one state or in the other. And so now you see what you have to do. You have to trace over the environment, because one never looks at the environment. And when you trace over the environment, you find that the density operator of the A plus M system is a sum of two terms, and you don't have any coherence anymore. You have a projector on the state 0A, 0M, plus the projector on the state 1A, 1M. So the only thing we can say is that with probability 1/2, we'll find one result, and with probability 1/2 the other, but you don't have any coherence anymore left between the two. And you see that when I have written this expression here, I have assumed that the state of the meter connects to the environment without entanglement. You see that in the final expression here is not entangled. So we implicitly assume here that the meter which measures a given observable has a fundamental property. It does not entangle with the environment. It leads to two states of the environment. And this kind of state, which does not entangle with the environment, is called a pointer state, a state which remains pure in spite of the fact that it is coupled to the environment. Let's take an example. Suppose that you are looking at a needle on the screen or meter. If you look at it, you will never see the meter being in two different directions at the same time. It's clear that such a meter is coupled to all the photons which are around are in different state for different positions of the meter. A different position of the meter corresponds to orthogonal state of the photon field, which means that these are good pointer states. All observers which look at the same meter will tell you where it is. There will be no ambiguity. So pointer states are so-called quasi-classical states, states that you want to describe by quantum physics, but you have to understand that they have a special coupling to the environment which prevents any entanglement with the environment. And so if you assume that, you find no longer the problem of the Schrodinger cat, and you come back to something which makes sense. But you see what happens, even if as time t equals 0, you assume that you have a pure state of the meter. Very quickly, it will couple to the environment and give you this final situation. And except in very special cases, it's very difficult, well, it's impossible to catch up the evolution of a system from a pure state to a mixture. And the phenomenon of decoherence is very, very fast. If you take a macroscopic cat, it will take to couple to the, even if you were able at time t equals 0 to put it in a pure state, it will take 10⁻30 or 10⁻40 seconds before it gets entangled with the environment, and you have a density operator instead of a pure state. And this is, of course, much shorter than the time it takes to kill a cat with any kind of little device. So you see that the situation, assuming that you have a pure state for the cat and that you will kill it later, is something which is completely impossible. And in general, it's the same thing happens for other kind of measuring devices. At the end of my lectures, next month, I will describe you an experiment that we did about 15 years ago, in which we were able to catch the very short time it takes for a very simple system, a field made of a few photons, to go from a Schrodinger cat situation to a classical situation. This is called decoherence. So now, very quickly, I want to tell you that this notion of partial density operator allows us also to quantify entanglement, to say whether we have a lot of entanglement or a very small amount of entanglement in a system. So you can quantify entanglement, and you can give a representation of entanglement in a very simple way using what we call the Schmitt expansion of a, and I consider just bipartite system which are made of two parts. So let's see how we can describe a system made of two parts. And first of all, I recall you what is the density operator of part A. This is just a sum of projectors on the state psi sub j, which are a set of orthogonal states, and the sum of the lambda j is equal to 1. So this is something that we have seen before. So let's now try to express the most general state of the combined system. You have to choose a basis of states. And what you can take, since you have already a basis of state in A, which are the lambda, the phi j, you multiply it by a basis, any basis of state, which I will call mu b in the other system. And you see that the most general state will have, if I have n, dimension n in the first system, I will have n squared terms, which are the tensor product of the basis in A by the basis mu in the other system. Now, so I have this expression, which is just what I said. But now you see in this double sum, which involves j and mu, you can take one value of j and sum over mu. And the sum over mu for a given j give you now a state of B, because it's a superposition of state of B, which are labeled with a given j. So I can, in this way, I can isolate for each j a kind of mirror image in the other system, which is the sum over j state over mu state, which I have written on the board. And what you can find very easily, which I just demonstrate at the top of the next column, is that the mirror states j on the other state on part B are orthogonal to each other. I call them j tilde. So to each j, I have a mirror image j tilde, which is defined by the equation that I've written here. And what I show here, very simply, because of the orthogonality because of the fact that rho is diagonal, I just show that the j tilde states are orthogonal to each other. They are not normalized. You get lambda j times delta jj prime. So if you divide by square root of lambda j, you get normalized states. And this is what I have written here. The j without the tilde are just normalized in this way. And then I have obtained this very simple form. The most general entangled state of two spins, of any system which may have a dimension n, is a sum of the square root of lambda j of a j in system with a mirror j in the other. And you see, it's a big advantage because now we have only n terms and not n squared terms. And it's much more easier on this expression to find out whether it is entangled or not, as we'll see in a moment. So you don't have to factorize a complicated mathematical expression, which is n squared term, and look for factorization. In this way, it will appear immediately. This is called the Schmitt expansion. And you see that it's a very simple expression, and it's symmetrical. So it shows you immediately that the two density operators of rho A and rho B are equal because they share the same set of the same spectrum. So when you have two parts which are entangled, if one is pure, the other is pure. If one is not pure, the other is not pure, and they have the same spectrum. So, and this allows us to define what is called the entropy of entanglement. You see, what is this notion? The density operator is given by probabilities. The lambda j are probabilities which sum up to 1, but they can be distributed any way between the different states. So it is similar to finding out how many distribution you can have of n particles between of a big number of particles between n boxes, 2 boxes if you have a spin 1/2, 3 boxes, and so on. How many ways you have to share a set of particles which should, a set of lambda which should amount to 1 among many possibility states. And this is given the entropy. By analogy with Boltzmann entropy, you define the entropy of entanglement by writing this expression by minus sum over the j of lambda j log of lambda j. And why did I write this? If you remember the first lecture that I gave when I looked at the number of distribution possible for n particles among j boxes, I got the same expression. So it's a natural way to define the amount of disorder about the knowledge I have of the different possible lambda j. So this is called the entropy of entanglement, and it's a well-defined quantity. So let's look at 2 extreme cases. Suppose that I have only 1 lambda different from 0. It's a pure case. If you compute the entropy, you will find 1 log 1, which is 0. So the entropy of a pure system has an entropy 0. There is no disorder. If, on the other hand, you assume complete disorder, it means that you have 1 over each of the lambda is 1 over square root of n, because the sum, each of the lambda is 1 over n, because the sum has to be equal to 1. So in fact, you find now that the entropy, the total entropy is 1, because I took the basis n. So log n of n is equal to 1. So the maximum entropy, the maximum disorder, leads to an entropy equal to 1. And you see that this corresponds to the state which is completely symmetrical. I have a 1 over square root of n of all the possibilities. Each j with its mirror image has the same probability. And you see that the density matrices are just 1 over n. All the values are the same. So there is no knowledge, absolutely no information in the density matrix. All the possibilities have the same probability. So you see that in the completely entangled state, you have no information in A and B separately. All the information is in the correlations between A and B. The last thing I would like to say before the break is to conclude by describing what happens if I have 2 spin 1/2. I've always taken this as a very simple example. You see, if you take 2 spin 1/2, the Hilbert space has a dimension 4. So the most general state of 2 spin 1/2 is written by an expansion of 4 states. But you see that if I use the Schmitt representation, I can reduce this to 2 states only. Because what I have to do is to choose 2 states for A and to take 2 mirror images for D. So the most general state I can take is to take an arbitrary direction for the first spin. The 2 states are spin up and spin down in that direction. And I choose the same thing for the other spin in another direction, spin up and spin down. And I couple them in a Schmitt expansion. And the last thing I can choose is the value of lambda. I take square root of lambda here and square root of 1 minus lambda for the other, so that the sum is equal to 1. So this is the most general state of 2 spins. And now if you compute the entropy, you find that the entropy is 0 here, pure state, the first pure state. And here it's 0 again, because it is the other state. And if I am just in between, if lambda is equal to 1/2, I have the maximum entropy. So let's look now at the maximally entangled state of 2 spins. And I write it in a choose a very simple basis, which is called the basis of Bell states. Bell being a physicist whom we'll be talking about in the second part of the lecture. You have 4 Bell states which are maximally entangled. And I have written them here. Psi 5 plus or minus, and psi plus and minus. 5 plus and minus are the state 0, 0 plus or minus 1, 1 in these 2 directions. And psi plus and minus bs are the term 0, 1 plus or minus 1, 0. So I have 4 states. And I remind you the results that we obtained last week. 3 of these 4 states correspond to a total spin equal to 1. That's phi plus and minus and psi plus. And psi minus is antisymmetrical by exchange, and it is a spin 0 state. And you see one property of the spin 0 state is that if you make any rotation on it, since it has a spin 0, it remains invariant. So you have 3 states which evolve like spin 1, and 1 state which under rotation is completely invariant. These are the Bell states, which are the maximally entangled state of 2 spins. And we see that these 2 states play a very important role in teleportation and in other quantum information stories. So, and I will stop here to make a break of 10 minutes, and we'll resume at